let's get into a numerical example with the log normal distribution and illustrate what the calculations are like. And they tend to be somewhat intense only because of the transformations that we have to make. The actual lookup in the tables are really not that big a deal at all because it is just the normal table, but manipulating our information is what really kind of gets us all to work. All right, let's look at that very direct mechanics of materials example where we're going to look at the axial strength of the bar as equal to its yield strength times its cross-sectional area. And physically what we're doing here is just the uniaxial case of pulling on a bar, and we produce this bar out of material such as something similar to A36 type steel, and S here is our yield strength, and through a variety of studies that have performed, we know that that is a log normally distributed strength where its median value has been found to be about 40 KSI. Right, now that's not the same thing as what you take oftentimes when you're dealing with A36 steel and you say, oh yeah, the yield strength is 36 KSI. That's in a deterministic calculation. You would use a different kind of number here, and this is going to be a probabilistic one, so a little bit different. Median value of 40 KSI, and the standard deviation of the log of that yield strength is 0.1. So not sigma s, but sigma lns. Right? The other random variable here is our member cross-sectional area. It also is log normal, and partly to help deal with how this information would typically come at us, and also to illustrate different manipulations of the transformation equations for these parameters, we'll let this be the mean of the area, not the median, but the mean is equal to 1 square inch, and the standard deviation of that cross-sectional area will be 0.05 square inches. Right? And if we were doing this in a deterministic way, we'd say, okay, the yield strength is 40 kips per square inch times the cross-sectional area of 1. 40 times 1 will give us a number of 40, and the units then become kips. Remember, kip is a 1,000 pounds, so our strength would be 40,000 pounds if we were doing this deterministically. But we're not, and we're going to account for random variability, and so therefore ask the question, then what's the probability that our capacity, our yield strength, is less than or equal to 35,000 pounds, or 35 kips? In order to address that, there are a couple of other key statistical parameters that we need. One of which is we need to know if there's any statistical dependence between the material property and the manufactured bar's cross-sectional area. And the answer to that is no, there's not. So those are statistically independent. And since we have a product of two log normals, then what we end up with is that F is also log normal. Again, specifically because it is the product of two independent log normal variates will produce another log normal variate. And so asking the question, what's the probability of the strength being less than or equal to 35 kips, can also be asked in the form of what's the probability that the natural log of our yield strength of the bar in force is less than or equal to natural log of 35. And we do that manipulation because we recognize this log normal property that is resulting. And when we do that, we end up with a normal calc. Hence, again, why we like to use the log normal model, because we can ultimately get ourselves to calculations after we do transformations that are straightforward, simple, and easy to look up. Okay. In order to do that, though, we're going to have a couple of parameters of f. In particular, we're going to need to know the mean of the natural log of f, and we need to know the variance of the natural log of f in order to do that transformation to the standard normal variate. So that's what we'll do first in our solution, is to go after then transformations where we recognize that the mean of a sum is equal to the sum of the means, right? So the mean of natural log of f is equal to the mean of the natural log of s plus the mean of the natural log of a. And we know that the variance of the natural log of f, in this case, the variance of a sum is equal to the sum of the variances, and only that because we don't have any covariance. These are independent random variables. There's no correlation, and later in our next module we'll introduce what to do if we did have some sort of joint information to have to deal with. Okay, so these are the two properties we need to have, and we're going to skip a line here because I'll come back with numbers. I'm going to put the numbers associated with these guys right directly in line there. Right. So let's go after the mean of the natural log of s. And we come back to our transformation equations that we were talking about a little bit before. Notice that the mean of the natural log of y is equal to the natural log of the median of y, and that's what we have for our s value. So we can go right directly at that one. And so the natural log of the median of 40 is going to be a fairly long number, 3.68887. I'm going to keep a ridiculously long set of numbers here. Excuse me, that last one is, oh, that's right. Not sure? Well, heck, let's check it out. Natural log of 40, 3.68879. Right, so we really could be rounding even this last one up to another 8. Right, so that's one of them. The other one, the variance of the natural log of s, is going to be 0.1 squared, or 0.01. So there's two of our numbers. Let's get those on up. Here's our 3.68888 and our 0.01. Right. Next, we got to work with the mean of the natural log of a, and we're given the regular mean of a and the standard deviation of a. Okay, so the mean of a, again by the transformation equation, this will be the second form of that, so that'll be the natural log of the mean of a minus 1/2 of the variance of the natural log of a. Well, we've got the first one, that's the natural log of 1, but we don't have the variance of the natural log of a yet. So let's get that one, and that's given to us by the natural log of 1 plus the coefficient of variation of a squared. Right, so that is the standard deviation of a divided by its mean, and then that quantity squared. And it'll turn out when we do that calculation that that's going to be equal to 0.0025. Not sure, don't believe me? Well, let's do it real quick. So that's the argument inside the natural log. Take the natural log of it, and there you go, 0.0025, 2496880. I'm going to cut that off at 0.0025. And notice that that actually turns out with this small coefficient of variation, that the natural log of 1 plus this small number is going to turn out to be that small number. And that's a very useful identity approximation later on when you do derivation work to help make some of this go a lot quicker and easier. So put this back up into the previous equation, and you end up with then natural log of 1, of course, is 0, and you end up here with minus 0.00125. Right? That is the mean of the natural log of A. So minus 0.00125. Now you see why I kept so many of these digits up here. And so 3.68888 minus 0.00125 is going to be equal to 3.6876. I'm going to keep 4 digits there. And then we have the variance calculation up here, 0.01 plus variance of natural log of A, that was the 0.0025. And so that equals 0.0125. And our two parameters really of value of interest to us are those two right there. Okay, and that gets us set up to do then our normal calc. We were after and interested in the probability that the natural log of f was less than or equal to the natural log of 35. Right, now we're in the normal space, so we can go and take a look at our transform variable z being the natural log of f minus the mean of the natural log of f divided by the standard deviation of the natural log of f. Right, and in this very specific numerical case, then our z star that we're going to go work with is natural log of 35 minus the mean of the natural log of f, that was our 3.6876, all divided by the standard deviation of the natural log of f, that's the square root of 0.0125. That's where a lot of people make their initial mistake, although it tends to be revealed pretty fast because you'll get an enormously large z star when you let this number here be too small. And that is usually off the tables and is a hint that, oops, you made a mistake, you forgot to do the calculation there. And so here's our mean of the natural log of f. We got 35 natural log minus that number, and then divide by our standard deviation, and we get a minus 1.18. Right, now I chopped off, truncated here, rounded to the second digit because our particular set of normal tables in your textbook it only go to that. Right, so our probability of natural log of f being less than or equal to natural log of 35 is our cumulative normal distribution function evaluated at minus 1.18. And if you really wanted to do linear interpolation, you could, but there's a number of reasons why you'd want to believe you don't have that much accuracy. And this will turn out, when we look it up, to be 0.119, or almost 12% chance. Of having a capacity less than 35, right? Dramatically different than when we might do this from a deterministic kind of perspective, where we would have said if you use the median values, oh gee, 40 times something would have given us, well, just straight these numbers, even though this is not a median. You might have said, though, 40 times 1, hey, I got 40 kips. Huh, absolutely, I'm greater than 35. If you would have said, well, wait a minute, you told us before, oftentimes when you use A36 steel, this number turns out to be 36. Again, 36 times 1, and you say, oh, I got enough strength if 35 is your demand. Well, it turns out that, yeah, you might have enough strength. At least you might have enough strength that 88% of the time you do, but 12% of the time you don't. And so one of the questions that ultimately will get asked is, well, is that a sufficient reliability, or is that likelihood of failure if 35 is our demand, is that acceptable? And typically I'd say in your civil engineering application, no, that's quite a large likelihood of failure. We're oftentimes looking at much smaller likelihoods of failure for your typical civil engineering situation.